Okay, our next topic is thermal conductivity of gases. We know that the temperature and hence the thermal energy varies from layer to layer of the gas, and there is a transfer of energy from one layer to another. The thermal conductivity of gases can also be explained on the basis of kinetic theory of gases. Now, the coefficient of thermal conductivity, which is represented by K, of any material is defined as the quantity of heat energy conducted in the steady state through unit area per unit time per unit temperature gradient. This is the definition of coefficient of thermal conductivity, which is the quantity of the heat energy conducted in a steady state through unit area per unit time per unit temperature gradient. Now suppose if d theta upon dz is the temperature gradient along the material, the quantity of heat conducted through the unit area in unit time is given by, according to definition, Q equal to K into d theta upon dz. Now expression for the coefficient of thermal conductivity of gas. Now consider three layers of gas such as A, B, C parallel to plane XOY. They are separated by distance lambda, the mean free path of the gas molecules. Let theta be the temperature of the gas in the layer A. If the d theta upon dz is the temperature gradient along z axis, therefore the temperature of the gas in the layer B will be theta plus lambda d theta upon dz आणि त्याच्या खालचं theta minus lambda d theta upon dz. Okay, along C. Therefore, though the molecules are moving along random in all direction, it can be assumed that about 1/3 of the molecules are moving along each axis. जे आपण मागच्या याच्यात बघितलेलं आहे. 1/6 can be assumed to be moving along positive direction and 1/6 along the negative direction of the coordinate axis. Now suppose let n, small n, be the number of molecules per unit volume of the gas, and m be the mass of the each molecule, and c be the RMS velocity of the molecule. Then by considering the unit area in unit layer in layer A, then the number of molecules from layer B crossing this unit area A in unit time in the direction downward direction is 1/6 NC, जे आपण मागच्या वेळेस बघितलं तेच आहे, and corresponding mass transported will be 1/6 mNc. Same equation असणार. Therefore the total heat transported by the molecules moving downward from layer B and crossing the layer A per unit area per unit time will be, त्याला फक्त mNc upon 6 इंटू या ठिकाणी टर्म घेतल्या CV इंटू थीटा प्लस लॅम्बडा डी थीटा अपॉन dz. मागच्या याच्यामध्ये फक्त ही टर्म नव्हती CV, बाकी सगळं सेम होतं. वेअर CV इज द स्पेसिफिक हीट ऑफ द गॅस ॲट कॉन्स्टंट व्हॉल्यूम. Similarly, total heat energy transported by the molecule moving upward from layer C and crossing the layer A per unit area per unit time will be mNc upon 6 CV into theta minus lambda d theta upon dz. वरच्या यात प्लस आहे, खालच्या यात फक्त मायनस आहे, आणि फक्त आता ही इक्वेशन आपल्याला काय करावं मायनस करावं लागेल नेट हीट एनर्जी ट्रान्सफर फाइंड आउट करण्याकरता. देअरफॉर द नेट हीट एनर्जी ट्रान्सफर पर युनिट एरिया पर युनिट टाइम इन डाउनवर्ड डायरेक्शन विल बी Q इक्वल टू, त्याला मायनस केलं आणि इक्वेशन मिळालं 1/3 mNc CV लॅम्बडा डी थीटा अपॉन dz. Now comparing equation 1.6 and 1.7. Equation 1.6 आपल्याकडे आहे Q equal to 1.6 K d theta upon dz, and 1.7 that is this equation. Therefore we get here K d theta upon dz equal to 1/3 mNc CV lambda into d theta upon dz. ते कॅन्सल होणार आणि आपल्याला मिळणार K equal to 1/3 mNc CV lambda, that is equal to 1/3 m into n, that is the density of the gas, that is 1/3 rho C CV lambda. And from equation 1.5 and 1.8, that is here equation 1.5, that is equation here 1.5, मागच्यात बघितलं होतं आपण eta equal to 1/3 rho C lambda. या इक्वेशन आपण फाइंड आउट आपल्याला मिळते इक्वेशन K equal to 1/3 rho C lambda into CV, that is 1/3 rho C lambda, that is equal to eta, that is K equal to eta CV. That is the we get equation for K equal to eta CV. As the variation in CV with changes in pressure and temperature is very small, The variation of K with pressure and temperature is small, similar to variation of eta with these physical quantities, and therefore K is independent of pressure but is directly proportional to the square root of the absolute temperature. Okay, by this equation here we know that K is directly proportional to the square root of the absolute temperature.